Hello folks, my name is Sam Chandrasekhar. I'm a program manager on the Azure Stream Analytics team, and today I'm going to talk to you about unlocking real-time predictive insights from your Internet of Things. Now this here is an IoT sensor. You could have a scenario where a building like this has several thousands of these that is constantly sending in data in real time to the Azure cloud. To be able to extract and unlock the full potential of IoT, you'll essentially need a stream processing system to analyze things on the hot path. And the large majority of today's talk is going to be focused on the IoT analytics story for the hot path through Azure Stream Analytics. When we speak about unlocking insights in real time, the key here is the time to insight. The past was all about waiting for data to get to some sort of a static repository before you could ask questions about it. Because the time to insight is so very critical, we're now beginning to ask questions on data that is in motion. So if you think of this as an analogy, if you want to count the number of cars in say, a square area or on the roads, you can take a snapshot of things in time and then count it. Or you can have a toll booth that constantly reads off of license plates or other attributes of the car and makes a count of these cars as they move. So that is the key notion here with streaming, the fact that you can ask questions on your data that is in motion. The other part that I'd like to highlight is these insights that you get from data that is in motion are sometimes perishable. There's a window of opportunity in many cases to act on these insights. For example, we have customers in Dubai that deploy building management solutions that read off of sensors just like this. And they have a very tight SLA around a few minutes to act on certain aberrations or anomalies in their data coming in so that they can make calls to emergency services if the temperature or the humidity numbers are out of whack. Looking at what we saw earlier, one might be going out right now, but just one sensor. If we had plenty more. When it comes to real-time stream processing, there's been this notion of simple event processing where you do simple things like filtering, transformations, enriching your data, etc. And then there was this notion of event stream processing where you do all of that, plus you aggregate your data, and then you add a bunch of rules. But what we're really talking about right now is complex event processing, where you can get multiple events, multiple data streams, and ask questions about these events by correlating things, by joining these things, by combining them, by looking up, by performing real-time scoring using machine learning models, and all of that. When it comes to the scenarios, there are two broad categories. There are things that you can do with human actors, where you have a bunch of humans who are looking at a live visualization, a live dashboard, and are making actionable decisions based on what they see. Or you can have a scenario where a machine is automating everything and taking actions and sort of automating the end-to-end loop, getting rid of the human in the picture. I'm going to switch over to a demo here. So I'm going to pull up a Power BI dashboard. And this is essentially going to show you a real-world view of an Internet of Things scenario in action. So we have a bunch of partners in the airplane engine space, as well as we have lots of airline partners. And in many cases, they're super interested in the field performance of a device. One area where IoT is causing a big disruption is in business models. We no longer see the same story of a device manufacturer selling a device to an end customer, but in many cases that they're essentially leasing out the device or selling it as a subscription. In the case of airplane engines, they're selling thrust towers to many airlines who get the determinism associated with the services without the headache associated with maintenance and servicing and things like that. So what I have here is an example scenario where we have a bunch of historical data that we have captured and we're replaying in real time as if it were happening right now. And now we're using Azure Stream Analytics to essentially look at the number of alerts going off for every specific engine part. So in this real-time dashboard that is updating as we speak, I can click on every engine part, and then it'll show me the number of alerts for that specific part. Now, this is interesting from the perspective of a human looking at it, but there are also actionable suggestions that I can get here, where you have a machine learning model that's working under the covers that's taking advantage of all of this data to essentially come up with predicted remaining useful life for this airplane part. And as a result, you can take downstream actions such as replacing this engine with another one, or just retiring this, or just continuing to let it stay. So from the perspective of a device manufacturer that is interested in such a model like device as a service, the key here is to be able to intimately be familiar with the field performance of your device. And what we see in the IoT space is that they're literally carpet bombing almost every aspect of their device with sensors that are constantly streaming out telemetry and instrumentation data that we can then reason about in the cloud to make actionable decisions that can hopefully unlock business value. I'm going to switch back here. So the three canonical scenarios for IoT analytics that we see is one where you enrich the data and you preserve it for future processing. There is this notion of a Lambda architecture where there is a hot path where there is data streaming out of your IoT devices, and you're asking questions about the data in motion. In addition, you can capture that data in some sort of a cold storage where you can throw powerful machine learning algorithms at it. And for scenarios where time to insight is not as critical, you can get both hot path insights as well as cold path insights. And that is one of the possibilities with the streaming solution that I'm talking about, because you can not just ask questions about it in real time, but you can also archive it in an enriched format for asking questions about it in a batch manner. The other big scenario is real-time dashboarding and live visualization, the kind I showed you. And the third one is kicking off workflows based on certain criteria. So typically what we see is for building monitoring systems, we have anomaly detection machine learning models that are performing scoring on real-time data that is coming in. And if there is an anomaly, then there is a workflow triggered off. One example of that could be emergency services could be alerted, or maybe a human operator is alerted. So those are the three canonical scenarios. When we look at sort of the overall architecture of the pipeline, we have data exhausts, which are IoT devices that are either sending in data directly to the cloud, or they're going through certain field gateways or other web or other intermediate boxes to perform translations. And then they're arriving into these event queuing systems and stream ingestion mechanisms. Azure provides this service called Event Hub, which is essentially a low latency distributed message queue. There's also another service called IoT Hub, which is more specifically tuned just for IoT devices. The difference between Event Hub and IoT Hub is that IoT Hub provides a bidirectional interface, so you can not just read stuff off of it, but if you're talking to a device, you can also issue commands back that go on and perform actions on that device itself. We also have the ability to ingest in reference data, and we'll talk about a few more examples. And we have a stream processing system. In this case, it is stream analytics. It could be other stream processing systems too that can potentially call out to machine learning. And then you have a plethora of output options for either archiving or for real-time dashboarding or to kick off automated workflows. Now, if we look at the ingredients of a streaming solution like this, there is a lot that will need to be done. Such as, you need to go, if you were to roll out something like this from scratch, you might want to procure the infrastructure, set it up, define your clusters, define out your topologies, deploy things, have mechanisms for reliability, high availability, scaling things, have connectivity to ingress sources, to machine learning solutions, have mechanisms for monitoring, troubleshooting, etc. Now, the benefit of Azure Stream Analytics, the solution I'm pitching here, is that all of this is taken care of. It's a fully managed service. It comes with an enterprise-grade SLA of 99.9% availability, satisfies most major compliance stipulations around the world, as well as providing a very friendly declarative SQL-like query language that provides temporal semantics. And I'll talk about the temporal nature and the temporal semantics that it provides in a little bit, but I want to sort of call out a key differentiator here, which is programmer productivity. What I have here on the slide is 3 lines of Azure Stream Analytics code to perform a simple aggregation operation. And I'm looking at the equivalent in Apache Storm, where you'd have to write over 1,000 lines of code just for that. So the key here is the programmer productivity through a declarative SQL-like programming language. Out of curiosity, how many of you would like to ask questions about your data that is coming in using SQL as opposed to a higher-level language? That's a healthy number. What about the rest? Do you all prefer high-level programming languages, or what does your solution look like? Curious. All right, I'll presume the rest of you are all Java developers. So at the end of the day, the pitch is that with Stream Analytics, you get the lowest total cost of ownership because it's a fully managed service for performing IoT analytics. When we talk about event stream data and IoT data that is coming in, a large part of what is involved here is the temporal semantics. All events are associated with a timestamp, and you're asking questions about data with the context of that time component. So there are a lot of temporal semantics, and we'll go over each one of these in some detail during the course of this presentation. But as an overview, we support the ability to have timestamps for application ingestion time. We have windowing functions. We have policies for event ordering, policies for dealing with late arriving events. We have the ability to join multiple streams, as well as combine it with data at rest. This is just a sampler of SQL constructs. So what we have done is we have taken conventional SQL and we've enhanced it with our own additions, such as windowing functions, such as geospatial functions, and other aggregation functions that might be relevant for streaming-related scenarios. Spoke about this. It's available in a bunch of Azure regions. So to illustrate the capabilities of the query language that I'm talking about, let's sort of take a specific scenario. And the scenario here is a toll booth, where you have a bunch of cars coming into the toll booth and a bunch of cars going out of the toll booth. So there are sensors that are reading, RFID-based sensors that are reading artifacts that are on these cars that identify a whole bunch of information. So most real toll booths that we see typically have 2 sensors, one at the entry and one at the exit. So I'm going to have 2 tables here that represent the entry stream and the exit stream. And the data collected here is shown here. Toll ID specifically refers to a certain identifier that explicitly references each toll booth. If there are multiple lanes, there are typically multiple toll booths. And then I also have a bunch of data at rest, reference data, such as commercial vehicle registration data, which does not actually change over time, but this is data that is lying around and constant and stuff that we can use for interesting scenarios and join with. So using our SQL-like query language, I can ask questions about the data coming in, such as this. So for example, I can say, I want to perform a filtering scenario where from the incoming stream, I want to find vehicles that are from specific states and meet a certain bunch of criteria. So I can specify that conditional branching logic here in my, I can specify that filtering logic here in my SQL statement and get those answers out in real time. What I can also do is perform joins. So in this case, I'm asking the question, find the time in seconds required for vehicles to pass the toll booth, and then report this. So if you notice here, there's a join condition. And this is joining on toll ID. So both the events, the entry stream as well as the exit stream have a toll ID, and I can perform a join on that, and I can also perform a temporal join. So if you notice, there's a function called dateDiff. Because it is events that are all associated with a timestamp, I'll need to specify a window of time during which this join operation ought to be done. And that is what the dateDiff line, the very last line of that SQL statement, performs. The other thing that I want to tell you here is there's another keyword here called timestamp by. Timestamp by essentially allows you to override the default behavior which looks at the NQ time of each event. So there are two timestamps here. One is the time recorded at the toll booth where an RFID tag was read and a certain time was recorded. And the other time here is an event getting NQ'd into Event Hub or IoT Hub. So by default, we look at the NQ time, but if you want to override that with a custom field that is a part of your data payload, you use the timestamp by keyword. And essentially, that's exactly what I'm doing here. I'm using the timestamp by keyword to look at the entry and exit times that are a part of my data payload coming in. And then I'm performing a join on that specific field using this dateDiff component to perform, to essentially stipulate a time bounds on that join. I'm also having another dateDiff component in the select statement itself, and that is to report the difference between the ingress and the egress times, which is what the goal of this query is, which is to find the amount of time vehicles spend between the entry and the exit checkpoints. So things like this. So if you imagine rolling out a bunch of code that from scratch to ask questions about this from on real-time streams of data, it would take several hundred lines of code. By having declarative SQL, you can answer complex questions like this on real-time streams of data that are coming in from IoT sources in near real time. I can also perform things like left outer joins, which are super useful for helping identify and detect patterns. In this case, I'm saying report all cars that have entered the toll booth but not exited within 5 minutes, so maybe they're stuck there. In which case, I'm doing a left outer join on these two tables, the entry table as well as the exit table. And when the criteria is one of these fields is null, that detects the absence of an event. So essentially what I'm looking for here is an absence of an event. And the left outer join is super useful for detecting patterns such as absence of events. And that is what's being detected here. One more example, expired registration. And for this, I'm using something called reference data. So we had a table that I showed you earlier that has commercial vehicle registration data. So this is data that can be assumed as things that don't change frequently. This doesn't have to be an input stream of data that is coming in from an IoT device. This is, for all practical purposes, constant data that you can look up. Using Azure Stream Analytics, you can join your incoming stream with some static data that you have that you can ingest using Azure Blob Storage, and you can have a join condition here saying, I think the join condition here is based on license plate, and if it is expired, which is a criteria of your reference data database, or which is a field that is stipulated in your reference data database, then you know it's an expired car, and then you can trigger off downstream workflows to deal with that. There's also the possibility of union. We'll get into that in some course, but the other thing that I want to bring up is windowing concepts, which is super critical and an important part of our query language. Since everything associated with event streams is associated with time, dealing with time windows is super important. We have 3 kinds of windows: sliding, tumbling, and hopping windows, and we'll go over each. They're used in the group by clause of your SQL-like statement. I call it SQL-like. We've modified the SQL language. We have our own name. We call it Stream Analytics Query Language, SAQL. but this is an offshoot of T-SQL. So let's look at tumbling windows first. So let's say you want to ask the question, every 10 seconds, give me the count of vehicles entering the toll booth over the last 10 seconds. So you want to ask a question on your real-time data stream, and you want to get an answer every 10 seconds. So you have this window that repeats itself, and you can stipulate the size of the window. The size of the window itself is fixed, and at the expiry of the time duration of each window, an output is generated. So in this case, there's the query. You'll notice that with the group by clause, there is a tumbling window field. So you can say, you can stipulate the size of the window. You can go as large as a day even. So this is 10 seconds, and it repeats itself. We also have a hopping window. Let's say you want the same result, but at a more increased frequency. There is an overlapping component here. Again, so there are two attributes to a hopping window. There is the length of the window, and then there is the frequency at which you want the outcome. So this will essentially, this query right here is similar to the query that we just saw for the tumbling window, except that you want the same answer more frequently. In the first case, we were looking at, give me a count of vehicles entering each toll booth over the last 10 seconds, and you wanted that every 10 seconds. Here you want it every 5 seconds. So there's an overlapping component to account for the increased frequency. And then there's also another unique window called a sliding window, which is used for looking around a specific event occurrence to look for patterns. In the case of a sliding window, an event is generated, or an output is generated every time an event either enters or leaves the system. So the sample query here to illustrate this is, find all toll booths that have served more than 10 vehicles in the last 20 seconds. So for this, I'm using a sliding window of size 20, and I'm using the having clause to count the number of events exceeding 10. The key here is that a sliding window generates an output every time an event either enters or leaves the system. So what you can do is, if a certain event happens, you can look back over a certain period of time that you stipulate as the sliding window size, and then go ahead and ask questions about it. So that is the uniqueness of the sliding window. So let me pause here for questions in case there are any before I proceed. Sorry.
Very quickly, in these three examples, you've been looking for things in the last 20 seconds. What if I want to look for things for the next 20 seconds? If it is streaming data, I can potentially wait for it to show up and basically execute my query against data that is going to be coming.
Absolutely. So the question was, here we're asking questions about things that happened in the past. Can we also ask questions about things that will happen in the future? And the answer is absolutely yes. Let's look at this specific query right now. Maybe this one will help. So this is looking at it from the perspective of the present, looking back in time. But if I were to run the query right now, I would be launching out a window into the future, starting now. So let's say I'm at t equals 15 seconds at this very point in time. There's a window that is looking out into the future as well, where the same question is being asked. Does that sort of help answer your question?
It maybe does. I'm still having a hard time wrapping my head around, well, how long does this query know how long to run for?
Mm-hmm.
Running it now for the next 20 seconds.
Certainly. So with Stream Analytics, you can specify the size of your windows. So you can start off a window right now and say, this is a window of size 20 seconds. So a window will start from right now, and it'll go on for the next 20 seconds. And using sliding windows, if there's a certain criteria that's met, then in the future you can generate a corresponding outcome. Does that help clarify?
I think so.
Okay.
On the same note, could you simply modify the query and ask in your group by or where 5 seconds, then are going to happen 5 seconds from now.
I see. So the question is, essentially, another way to ask the question is, can I have variable-sized windows? And the size of the window going forward is specified by a variable
Which is, yeah, such as
that you specify based on runtime information that you get. The answer is, at this point in time, no. Windows sizes are fixed when you write the query. Using a number, you can specify it in seconds or minutes or hours, but the size itself at the time of authoring the query is fixed. But you can start off a window right now that goes out into the future.
But in my question, the window is constant, except that it's parameterized by function now that returns current size.
He's talking about a function or a keyword now, which means
Yes.
from the query,
Now.
whatever the time is right now when I hit the enter button.
So I'm saying now function plus 5, comma, now plus 10.
Right. So we have. So the question is, can I have a mechanism where I can somehow get the current time and use that as an input to kick off a window into the future? The answer is no. We do not support that right now. We have something called system.timestamp, which implicitly captures the underlying system time that you can use by default. But can you explicitly sort of say, what is the wall clock time right now, and then go ahead and trigger off something? At this point in time, we do not. Any other questions before we move on further? Go ahead.
Can you talk a little more about joining in reference data that is sort of largely static? Is that just defined as another input similar to the streams of data coming in?
So the question was if I could talk more about reference data, and there's a specific question around, is reference data treated similar to input events? From the perspective of the language itself, it is identical. The way you articulate a new event stream is identical to how you'd articulate reference data. In the case of reference data, there is no time component. So if I go to this example where, or in this specific example, that does not have a time component, whoops. Yeah. So in this case, I have reference data, which is registration data, and I'm just pulling this in as if it were another input stream, and I'm performing a join operation right there.
If registration data happens to be changing, if data is being added to that table behind the scenes, how is that represented in this model? At what point do you sort of fetch the latest query of the reference data?
So the question is, if my reference data itself is changing under the covers, what do I do? How do I articulate a refresh rate for my reference data to be refreshed into the system? And the answer to that is, if your reference data itself is changing, then specifying that as a reference data input source is probably not the way to go. The underlying presupposition with reference data is that it is infrequently changing, or for all practical purposes, constant. Things like registration information and things like that. The way it works under the covers in Stream Analytics is that every time you start a job, there's a bunch of reference data that is sucked up and held in a certain context, and that is being looked up. If there is a certain refresh rate, but that is not something that you can explicitly tweak. We have our own internal refresh rates. It's typically of the order of hours. So the guidance is, if your data is frequently changing, then you'd be better off articulating that as an input source, as an event data stream input, as opposed to reference data. Yeah, there's a question at the back. Can you say that again? I couldn't quite hear the question from up here. Okay. All right, we have one more question there before we'll move on.
How large can the window be?
24 hours. Question.
Can this thing be run locally? Does it have to be tied to Azure?
So the question is, can this be run locally? Does it have to be tied with Azure? The answer is no. This is an Azure-only service as things stand right now. For running things locally, if you want to get complex event processing and temporal semantics and things like that locally, we have this product called Stream Insight. SQL Server is the shipping vehicle for that. That provides a lot of this functionality for local computation as things stand right now. But this is specifically an Azure service. All right, we'll move on to other topics I have. Just in case the expressiveness of, or the capabilities of SAQL are insufficient for your needs, we also have custom code support, and we have this functionality in private preview right now, which is JavaScript user-defined functions, where you can essentially write custom code in JavaScript and have callouts from your Stream Analytics job. So here's an example. On the right, what I have is a bunch of metadata that you'll need to supply beforehand that sort of talks about the kind of JavaScript function and what it does and some of the properties associated with that. And on the left, you'll notice the usage of it. So in this case, I have hex to int that I'm calling almost as a function. I'm passing in a parameter. This is going as a call out to JavaScript that is essentially a user-defined function. We've chosen JavaScript first. If you have preferences for other languages, come talk to me, and we're eager to support more possibilities here. Again, this is just a small sampler of possibilities. We chose JavaScript because when it comes to string manipulation, when it comes to array manipulation and things like that, there was a rich ecosystem of calls that you could readily use. Again, we're all about programmer productivity. So if you can take advantage of something that already exists, then we're all about that. So if you have asked for more language supports, come talk to me, and we're happy to look at that and prioritize that. I have a slide on reference data. We talked about that already. The thing that I want to highlight here is that the only input source for reference data that we currently support is Azure Blob Storage. Yesterday, we got some requests for more sources. We're contemplating that. That is something that we're looking at actively, especially SQL Server as a reference data input. I want to talk about scalability. We have this notion of streaming units that is essentially a function of the compute footprint of your Stream Analytics job. When you think of a Stream Analytics job, this is a bunch of code that is running for perpetuity on inputs that are coming in. And streaming units is the currency that we use to measure the compute footprint of that. It is also what we use, it is also one of the things that we use for pricing. The service itself is priced as a function of the number of streaming units you consume every hour, as well as the volume of data ingested. Streaming units is, since it's a function of the compute footprint, you can also seamlessly add and remove streaming units and upscale or downscale your job based on the kind of needs you have. The other scalability aspect that I want to draw attention to is partitions. You have the ability to parallelly and concurrently run the same query on multiple partitions. Event Hub, as well as IoT Hub, supports the notion of partitioning. So for example, in the scenario that we just went over, you could have, let's say you had 4 toll booths, one for each lane of the road. You can have toll booth 1 sending data to partition A, and toll booth B sending data to partition B, and things like that. Or if you could think of a light bulb analogy, it would be the same. You could have a light bulb explicitly address a specific partition in Event Hub and send data just to that partition. And then we have the ability to deploy the same query to run concurrently on all of these partitions. And that allows you to fan out and be more productive. It's again parallel execution. And the example there specifies just that. So there is a partition by keyword that you'll have to use and a partition ID to specify. In this specific example that I gave you for the toll booths, there is a mapping between the partition ID, which is the event hub partitions that I'm referencing here, and the toll booths in question. So there's a mapping that you'll have to specify based on your that you'll have to specify in the logic that will send data to specific partitions, and that can be leveraged here as well.
What's the driving factor behind that? Splitting into multiple partitions.
So the question is, what is the motivating factor behind this kind of computation, splitting it into multiple partitions? There are quite a few, but at a high level, it is to perform parallel execution to get a higher amount of throughput.
But what is the base throughput that we're trying to consume, I guess?
So let
4 booths at one time. That's a single one.
so let's take the example. Let's say hundreds of cars are passing through each toll booth, and they're all sending data to, let's say, event hub is the choice of input. If you just had one partition, or if you were not using the concept of partitions, they would all sort of line up sequentially. So stream analytics, which is the component that lies after event hub, would have to pick up things one after the other. And you could have events from toll booth 1, and then one from toll booth 3, one from toll booth 4, etc. It is possible that in your processing logic, you also want to take advantage of that, and maybe you're outputting it to a Power BI dashboard or kicking off workflows, and you know of certain aspects of your input data. For example, in this case, let's say all the trucks on the road went to a specific toll booth, and you were doing something interesting downstream with that data. So as opposed to dealing with things sequentially and having some of the data to wait, you can have it go to specific partitions and have the same instance of that query run on each partition, thereby being able to get through that data that has come into your messaging queue faster. Does that answer your question? Sure. We also have the ability to articulate specific policies for out-of-order and late arriving events. Out-of-order events. So under the cover, Stream Analytics uses this notion of a reorder buffer, where based on the size of your window, we carve out a certain section of memory, and we wait for events to fill that up. It is possible that as events come in, they do not come in order because of network latencies, because of other logic that might be between the event generation as well as stream analytics. It's possible that the events don't arrive in order. And for that, we can specify offset policies to deal with, you can articulate how you can deal with that. Similarly, you can also have late arriving events because of clock skews, network latency, you name it. So you can say, hold up my processing until every event that is supposed to be, or that I expect in that certain window arrives, or you can say, I want to adjust it or drop it. So I'm going to give events a tolerance window of 5 seconds, and if they do not arrive, then I'm going to drop them and move on with my processing. Because at the end of the day, when you use windowing functions, we have a reorder buffer, and we don't proceed until the default behavior is we don't proceed until all of the events that are expected in that actually arrive. So you can choose to override that by explicitly specifying adjust policies or drop policies. And this is all articulated in the job definition. There's a question right here.
Suppose you have incorrect or corrupt data coming in from a sensor,
Mm-hmm.
and at that point you're not able to execute the job.
Mm-hmm.
But at some point later on, something else comes through the lag that allows you to calculate or impute that sensor.
Mm-hmm.
So is there any logic for handling those types of data quality dropouts, chatter, noise that happens in streaming data?
Right. So the question is, you could have malformed data that is coming in. Can you sort of do away with that? And once you get the well-formed version of it, can you go ahead and recompute? The answer is yes, but it'll take a lot of complex provisioning beforehand, where you'll have to expect this. What we do not have right now is this notion of a dead letter queue, where you have this malformed event that we hoard away elsewhere, and once a better version of it comes, we can replay it. We do not have that functionality, but you can essentially achieve the same functionality by stringing together multiple jobs, or having a job output to multiple event hubs, or by having windows overlap with each other. You can have a multi-step query with that sort of overlaps against the same time frame to achieve that functionality. Does that answer your question? There's another question.
So this is out of order or late arriving, meaning the event still shows up, right?
Correct.
If you're waiting on an event and it doesn't show up,
Mm-hmm.
is there policy control on that so I can estimate it or size it after a while and squeeze it in?
Absolutely there is. So if you look at that screenshot that I have there is something called adjust. So you can either drop the event and say, all right, you did not arrive within a certain tolerance window, so I'm going to say, I cannot entertain you and move on. Or you can adjust it by essentially rewriting the timestamp associated with that event to something that is inside your buffer that you're holding up. And then move on. So does that answer your question?
Sure.
Yeah. So those are, again, this is articulated at a job level granularity. So every Azure Stream Analytics job, which is this bunch of code that runs for perpetuity against your event stream, has a definition format, and you can. This is where this is articulated. We also have the ability to integrate with Azure Machine Learning through a callout mechanism. Again, it looks like a function call, very similar to the JavaScript UDF. The most common scenarios that we see here are anomaly detection and sentiment analytics for data that is coming in. You can have a machine learning model for whatever. You can roll out your own and call out to that model to perform real-time scoring. So I have a demo here where I have a bunch of Twitter data that is streaming in. Actually, let me try this. Why don't you give me a hashtag and we look up Twitter feeds for that specific hashtags? Data science, all right. All right. I'm going to say Ignite. So I have an app here that is essentially pulling tweets from Twitter using the Twitter API. So it's looking for tweets. I'm not sure there are folks trending about Ignite right now. So, all right, something came through. Why don't we pick something that all right, this seems to be slow as well. Let's try debate, all right? Nothing contentious, just debate. All right, there's no shortage of activity here. So what I have here is a Power BI dashboard. Oops. Give me 1 second. The question is, can we talk to Microsoft Cognitive APIs? The answer is right now, no. But that is something that we're looking at. That is something in our backlog as we speak
So like
right
on
now.
the roadmap, potentially you could stream it and then do something
Uh,
next.
uh,
Can't say it.
I will not confirm anything, but that is certainly an interesting possibility that we're actively looking at. All right, so this is sort of a sentiment classification of a bunch of debate-related data. Clearly, negative seems to be the largest section have the largest area here. So, number of negative tweets, number of positive tweets, number of neutral tweets. Again, there's a sentiment analytics model that I have hosted up in Azure Stream Analytics, sorry, in Azure Machine Learning, and that is performing real-time scoring. We also have pre-built models for this for anomaly detection, which is super common for IoT scenarios and use cases. The idea here is you make a function call out from your Stream Analytics job to that, and you perform real-time scoring on your data.
How do you write a function?
The function is like right here. So sentiment is the name of the function. So in the Azure Stream Analytics portal experience, there is a tab called Functions. You add that. You specify your Azure Machine Learning API endpoint. And it's a REST API made for every event coming in. There's a question, right?
Different from the stream, the sentiment that Twitter already provides. Do they have in their API? Do they have some sentiment score? Do you use that, or is it completely Microsoft?
So in this specific, so the question was, how is this different from the sentiment information Twitter already provides? The answer here is, for this specific example, we're ignoring that field. We have a sentiment analysis model hosted up in Azure Machine Learning that is based on one of the samples that we have in Azure Machine Learning, and we're going as per the text there and making sense of that. Now, it is true, I think, that in the Twitter API itself, there is a field that has some sort of a sentiment score. In this specific example, I'm not using that. I could as well use that. The purpose of this example was to demonstrate the fact that you can call out to a machine learning model, and that's what it's showing. The specific model that we have here is unrelated to anything Twitter is using. I'm not sure which one's better, but you could replace this as a placeholder for anomaly detection or any other model that you roll out yourself. Sorry, there was a question back there. Did I answer your question?
Yeah.
The previous one. All right, thank you. I'm also going to announce geospatial functions. This has been a long-standing ask from a lot of our customers. We now have geospatial functions in Azure Stream Analytics, and we have lots of examples and lots of scenarios that this unlocks. The most exciting scenarios are around geofencing, where we have this example where when a certain artifact leaves a certain geofence, a trigger goes off, an alert goes off, and then you can take downstream actions. Or it also unlocks a whole bunch of possibilities with connected car scenarios. We have auto manufacturers who are trying out scenarios of the nature where if a certain number of cars are performing hazardous braking operations or hazardous maneuvering operations in a certain section of roadway, then you can send out an alert to all of the other cars within a certain radius saying, there's a potential issue here, or there are potential hazardous driving conditions in this intersection and things like that. So these are scenarios that have actually been put into production. This functionality is in private preview. Feel free to come talk to me. I can help unlock that for your account. Just like the JavaScript user-defined functions, that's also in private preview as we speak. The other aspect that I want to highlight here is we also support, since we support output to Power BI, and Power BI has a Bing Maps component, you can do interesting visualizations with maps. I have a bunch of screenshots of the possibilities. I want to switch over to a demo here. So I have a couple of event generators. Oops. that are sending in events, GPS-related events for a fleet of trucks that are moving in. And I have an output here to Bing Maps where the intention is to perform a live visualization of this geospatial data. So this data is going through. We're getting data for the location of trucks. We're getting weather data. So what I'm going to do is I'm going to say all. So we'll hopefully see right now is some trucks showing up. I just refreshed the page. This itself is not running in Power BI yet, but it is certainly possible to have similar possibilities with Power BI. So what I have here is locations of trucks on a map, and if I zoom in close enough, you'll notice that the trucks are actually moving. The information about the truck, in this case, the only information about the truck that we're sending is its GPS coordinates and a certain ID. This is not reference data. This is streaming data that is coming in. Absolutely, absolutely. Are there possibilities to have additional information about these trucks as reference data? The answer is absolutely yes. So we have a bunch of data coming in. Whoops. Excuse me. I'm going to try and restart this one more time.
This is real time?
This is in near real time. So I have data that is streaming in from here. This is a data generator based on, it's replaying a bunch of data, real-life data that we had captured from elsewhere. And this is streaming in right now. So what I'm trying to show you here is the fact that I can ask questions about data that is streaming in real time from these trucks and show you a live visualization of the answers. So I have a bunch of tabs here in this demo. What this tab is doing is that it's essentially is that it's running an Azure Stream Analytics query under the covers. So when I say within Colorado, this is going to invoke a geofence using a Stream Analytics query and show me just the trucks that are in the geofence marked by Colorado. So if I go ahead and do that, I'm going to uncheck all. So you see that? There's one truck in Colorado. The reason I picked that is because if you look at the state of Colorado, it has sharp edges, so the boundaries are easier to model as you write out the geofence. Sorry, can you say the question?
Model the geofences yourself?
That is correct. I will have to model the geofences myself. If we go back to our geospatial functions, we have the ability to specify a polygon. You can specify a complex polygon. In this case, it's a four-sided polygon for the state of Colorado. But yes, you will have to specify the geofence yourself. I can also ask other questions. I can have a bunch of weather information that is streaming in, and I can perform joins on the weather information. Sorry, there's a question right there.
How small can a geofencing area be?
As small as, I forget the data type that we use for the GPS coordinates. I think it's a floating point that goes on up to several digits. I can follow up with you offline, but it is at a very fine granularity in terms of the smallest size square that you can draw. Did you have something specific in mind in terms of resolution? I see. Yeah, most certainly, most certainly. We've tried this with a bunch of toy robot cars, and it seems to work fairly well. So this weather data is loading in. Again, this is stuff that is coming in real time. And again, in the visualization, what I'm trying to show here is that the shade of red is a function of how hot it is. And then I can also ask questions saying, show me all trucks that meet this specific criteria, that are within Colorado and where the temperature is below a certain threshold. Pardon my unit of temperature used there.
If you have the geospatial, could you have some sort of, for geographic, geospatial, could you have some sort of reference data that you could query from that if someone said Colorado, you could
Mhm.
like, have that being as a city, they could do that potentially?
Absolutely. So the question was, can we have a bunch of geofences or standardized location data?
Is there public data available that you can query off of it and get the fence variables,
Mhm.
geofencing variables brought back?
The answer is yes, there is. But you will have to ingest that into your subscription, into Azure Blob Storage, and join it with reference data. So just for the purposes of the recording, the question was, can we have reference data sources feeding in geospatial information in terms of polygons or points and things like that? And the answer is absolutely yes. So for instance, what I could have done if I had the time and the diligence is that I could have gotten the geofences based on the GPS coordinates in terms of polygons for every state, and I could be asking more interesting questions here if I'd loaded them up into reference data. In this case, it's just a straight out join. Yeah. Question.
Many organizations have GIS shapefiles that they've created over the years.
Mm-hmm.
Is there a way that information could also be used or referenced in Azure, or is there a plan to get there in the future?
Absolutely. So the question is, can we talk to other GIS systems? The answer is the input format that we support is GeoJSON, and we deal with things in the currency of GeoJSON. So if you have anything that's in GeoJSON, we should be able to deal with that right away. The other thing is that the same underlying geospatial capability library that is in DocumentDB as well as SQL Server is what we use here, so you'll notice that consistency as well. Because in many areas, a lot of the aspects are left to implementation detail. So with DocumentDB and Stream Analytics and SQL Server, the underlying engine is the same thing. So you'd find consistency there as well. Does that answer your question?
Yeah, particularly shapefiles are the standard that we use.
I see.
NANSI standard, so that would be great.
I see. That's good feedback. I'm not aware of that. I'll follow up with you offline and we can take you up on that. So this is geospatial functions. The one last thing that I want to show you is also new functionality that we have with Stream Analytics. This is new monitoring and troubleshooting capability that we have with Stream Analytics. This is called the job diagram. This is also in private preview. So again, if you want access to the geospatial stuff, to the JavaScript custom code stuff, or this advanced monitoring capability, feel free to come talk to me. Essentially what this does is it breaks out your job and your streaming pipeline into a visualized set of blocks that you can play around with. We have sort of the semantic zoom capability where, if there is an input and it has multiple partitions, I can click on it and expand it out into partitions. I can also click on each of these artifacts and go look at metrics for each of those. I can look at the number of input events coming in, number of output events, the number of data conversion errors for each step and things like that, thereby allowing me not just to monitor a solution, but also to debug things when things go wrong. It is super useful for isolating out and localizing the source of problems. For instance, if I'm not seeing an output at one end for whatever reason, I can go open this up and see what step is receiving inputs and not putting out outputs, or if I'm even getting in inputs, things like that. This is in addition to the all-up Azure monitoring and troubleshooting capability that we have for job level metrics, where you can also have alerts based on certain conditions for metrics and things like that. There's one question. Correct. So this is to be seen as from left to right. We have data flowing in from event hubs, and that is going in through a processing query and outputting to Power BI. And again, I can break down the specific query to subcomponents of that and get metrics for each of those steps. I can choose to write my query with multiple steps and get metrics for each step. I can also say show properties, and it'll show me the corresponding code for that section of the query. So this is, again, new functionality in private preview. Feel free to come talk to me, and I'll have that unlocked for your subscription. When it comes to interacting with Stream Analytics, we have lots of modalities. You can surely use the Azure portal, both the old as well as the new. We also have programmatic access mechanisms through REST APIs, a .NET SDK, as well as the ability to use it with PowerShell. I'm going to end it by talking about a few customer stories. Honeywell uses Stream Analytics in production for a bunch of building monitoring scenarios. We have ThyssenKrupp, the elevator company, that uses Stream Analytics for performing predictive and preemptive maintenance on elevators. And we did a case study with them that goes over the amount of money they saved over as a result of doing this. Aerocrine is a medical device manufacturer that helps detect asthma by blowing into a specific device, and that sends data to the cloud, and doctors can take actionable things. NEC does targeted advertising in stores based on your proximity to specific beacons and things like that. Fujitsu in Japan has this farm where temperature and humidity conditions for farming are controlled in a super precise way to grow lettuce with certain amounts of potassium that are useful to folks with certain conditions. So this is a bunch of customer stories. I'll leave you with a call to action. What app could you develop if you could predict, detect, and adapt to live data instantaneously in near real time? So I'll end it there. I have a few more minutes for questions, so we'll take a few questions.
We'll go back to your thing about the stream unit.
Mm-hmm.
Can you pull them together like you do with DPUs to manage your spikes to where you know what your costs are going to be at the end of the month, rather than having them spike and not know where the spikes are going to be?
So the question is,
Across you said you could partition them.
Mhm.
Across the partitions, can you pull those partitions together with your stream units?
so the question is, can you aggregate streaming units across partitions and do some kind of auto scaling, perhaps? The answer is, right now, we don't do auto scaling per se, but what we do is we have a metric that to look at the percentage of streaming units that you're currently consuming, and you can alarm on those metrics and then take downstream actions that can kick off workflows potentially, such as send out alerts to change the number of streaming units. So some of that is on our plate, but right now we don't have a lot of that. So, question?
How the device send data to stream?
So the question is, how does a specific device send data to the Azure Stream Analytics suite? For that, I'll go back to the architecture pipeline that I drew up. So the device itself might be IP capable, or it may not be IP capable. So it might be connecting to a gateway. So either the device directly or through a gateway is talking to an Azure endpoint, which is Event Hub or IoT Hub. Sorry?
It's an API call.
It's an API call, yes. You can also have the SDK for that specific entity installed locally on the device to ensure that it addresses the right ingestion and queuing and message queues that Event Hub and IoT Hub provide. And then Stream Analytics is a component that sticks on to the other end of Event Hub or IoT Hub, or even blob storage, and then you can pick off data from there and then process it.
So is that an app that you're actually pushing
Yes, it is a bunch of code that you would write on the device to specifically send out data. Or in many cases, the device itself connects to an intermediate entity such as a hub or a gateway that is then, that has a bunch of code to go send it out to the right entities in Azure. Does that answer your question? We can chat offline if you have more questions. Any other questions or concerns, folks? Or any other aspects that you want me to address?
Just a quick note.
Mhm.
This was really great. And if you guys are interested more, if you go to Channel 9, just Google this Bing Channel 9 Microsoft. This will be up there as well. And there's also streaming analytics videos too, if you want to see tons of more information.
Absolutely. All right, thank you so much, folks. Yeah.